Okay, good evening everyone. I hope I'm audible. So our today's topic is Spearman's rank correlation. It's called Spearman's rank correlation. Okay. So first of all, we need to understand what do we mean by the term correlation. Correlation tells us the connection, the relation, the dependency of one variable to another. So let's say there are two variables, two quantities x and y. So by the numerical value of correlation, we get to find how are the two quantities connected to each other, how are the two quantities related to each other. That is the meaning of correlation. So correlation gives us an idea about whether or not two quantities are connected to each other. Let us take a small example. Suppose we need to find out whether the price of cold drinks depends upon the temperature. Okay, so if we note if we find out that the prices of the cold drinks increases with the increase in temperature, that means temperature and the price of cold drinks are directly correlated. In that case, the value of correlation coefficient would be more than 0, positive. If it is very strongly correlated, the value will be close to 1. Similarly, if we find out that the prices of the two quantities are inversely correlated, let's say the prices of temperature versus the prices of jackets or sweat t-shirts, or for that matter blankets. So more the temperature, less the prices of these articles. So they are negatively correlated. If the value comes out to be negative, that means if A increases, B decreases. Similarly, the value of rank correlation will be 0 when the articles or the items are just not correlated to each other. So that is how correlation works. I hope that part is clear. Does anybody have any queries so far? Okay. Now, the concept of correlation is dependent upon numerical data. So there are lots of information which we gather, lots of numeric data that we gather. Using it, we perform a set of operations, a set of calculations. Depending upon the values, depending upon the calculated values, we determine whether the correlations or the variables are correlated, yes or no. Now, in order to find something as simple as whether they are correlated or not, we need not necessarily do such cumbersome calculations over a series of data and find out whether they are correlated. Instead, what we can do is we can have a quick estimate of whether they are correlated or not using Spearman's rank correlation coefficient. Spearman was a mathematician, a statistician who discovered that the two variables will give a similar value of correlation coefficient using the concept of ranks instead of their actual values. What do we mean by that? We'll come to that in the next slide. Before that, let us quickly note down the formula of rank correlation. If you note that the formula of rank correlation is 1 negative 6 times summation of d square, where d is the difference between the ranking of each item. We'll come to the details in a couple of minutes. And n is the number of paired observations. N is the number of paired observations. Okay. Okay. Let us move on to the next slide. Okay. So let us try and understand this entire concept by the help of some data, some information, a numeric situation. Before we go on to that, does anybody have any doubt so far? Would anybody like to ask anything so far? Okay, so let's move ahead with the numerical example. In this example, we have already been given that there is a dance competition in which we have 8 candidates. The candidates are named from A till H. Now, according to Judge 1, he has ranked the candidates as per in the second column. So candidate A gets a ranking 1, candidate B gets a ranking of 7, and so on and so forth. Ranking 1 of course means he is the best judged candidate. Similarly, Judge 2 ranks the candidate A as rank 4, candidate B as rank 3, and so on and so forth. Now you can see there is some disparity between the judges. So we actually are trying to find out whether both the judges are making a similar kind of a statement, yes or no. Okay. So we are trying to find the correlation coefficient using Spearman's rank formula. So the first column in this table demonstrates the names of the dancers or codes of the dancers. The second column demonstrates the rank given by Judge 1. The third column gives us the rank given by Judge 2. And column 4 is basically the difference between the ranks, x negative y. How do we calculate? Very simply, 1 negative 4 which is negative 3. 4 difference 3 which is 4. Sorry, 7 difference 3 which is 4. 2 negative 6 which is negative 4, and so on. That is how we calculate the values of D. I hope this part is clear to everyone. Next we have the value of D square. We calculate D square by simply calculating the square of this term D. So negative 3 square becomes 9, 4 square becomes 16, negative 4 square becomes 16, and so on and so forth. 6 square becomes 36. When we find the sum total of this column, we get summation of D square equal to 128. Okay, that's the numerical value of summation D square. Feel free to ask me if you have any doubts so far. Okay, let's carry on to the next page. So we need to keep in mind the value of summation of D square, which comes out to be 126. Also, we need to remember how many set of data are there. If you notice, starting from A to H, there are 8 set of data, 8 pair of data. So our formula for rank correlation, this is Spearman's rank correlation, will be equal to 1 negative 6 times, this 6 is a fixed constant, so it's always going to be 6. So 6 times summation of D square. Our summation of D square is 126 if you remember. Number of paired observations were 8. So denominator would be 8 times 8 square negative 1. On simplifying this, we get a final value of negative 0.5. This means that the values are negatively correlated. Simple language, this means when Judge 1 ranks a candidate as a topper, the Judge 2 actually doesn't agree with him. So they are not in unison. Okay. So this is how rank correlation works. Let us take another look at it, a quick summary. So according to the data, according to the table given to us, there are 8 dancers available to us. For these 8 dancers named A to 8, Judge 1 gives them these ranks, Judge 2 provides them these ranks. The difference between the ranks is denoted by small d, that is x negative y. So we simply subtract 1 minus 4, negative 3, 7 minus 3 gives us 4, 2 negative 6 gives me minus 4, and so on and so forth. Once we find the value of d, we can quickly find d square, which is simply negative 3 put to the power 2, 4 put to the power 2, minus 4 put to the power 2, and so on. As soon as we get the value of d square, we can quickly find the summation of d square, which comes out to be 126. At this stage, we need to remember the numerical value of d square and the number of paired observations that we have used so far. So if you remember, summation d square was 126. We multiply 6 with that. 6 is a part of the formula. Number of data provided to us is 8. Number of paired values is 8. So my formula is 1 negative 6 times 126 divided by 8 times 8 square negative 1. Simplifying which we get negative 0.5. This means the variables are negatively correlated. So they do not agree with each other. The judge A and judge B are not agreeing to each other. They are pointing in different directions. Okay. Okay. So if anybody has any question, feel free to ask. We'll move on to the next point after this. Okay. So Spearman's rank correlation coefficient can take the following values. The values lie between -1 and +1. When we get a value of +1 for R, it indicates it's a case of perfect positive correlation. Means both the judges are totally agreeing with each other. If the correlation value comes out to be 0, it means there is just no correlation between them. They are, not making sense. And in the third case, if the value comes out to be -1, it simply means that the judges have totally different opinions altogether. Okay. Now, it is possible in certain situations that we have a case of tied ranks. So let us take a quick short example to understand what do we mean by tied ranks. So it is possible to have numbers like this: 1, 2, 2, and 3. Or let's say 10, 20, 20, and 30. So how would we rank these four numbers? When we try to rank these four numbers, it is quite obvious that the number 30, which is the largest, has to be ranked 1. That part is quite obvious. So we now understand that 30 has to be ranked 1. But what about 20? What about this 20? Another thing is quite sure that 10 has to be ranked 4. But again, the question mark is with these two. Since these two are tied, we are not sure which one to put as rank 2, which one to put as rank 3. Instead, what we do is we give or we allot both of them a rank of 2.5. So the ranks now become 1, 2.5, 2.5, and 4. I hope that makes sense to everyone. Let us take another example of tied ranks. Another example of tied ranks would be, let's say we take numbers, this time 10, 20, 20, again a 20, and 40. So needless to say that rank 1 would be 40, rank 5 would be 10. The score of 10 would be given a rank 5. Now all these three have a common score, have an equal score, so they have to be given an equal rank. Now one of them should have been 2, one of them could have been 3, one of them could have been 4. So we take the average of these three numbers, which is again 3, and we allot the rank 3 to all three of them. So this becomes rank 3, this becomes rank 3, this becomes rank 3. So what are the ranks in this case? It is 1, 3, 3, 3 and 5. Okay, so this is a case of tied ranks, when the ranks are equal to each other. This is how we deal with tied ranks. Okay, in case of number of tied ranks, the formula takes a small turn, a small twist from the original formula. Okay, before we go on to the formula for tied ranks, let us quickly have a look at the formula for the normal case, the one that we did a few minutes back. Let us have another look at that formula, and then we'll compare it with the tied ranks formula. The formulas are quite tightly coupled, they are quite similar to each other. So please note the formula for a normal case of rank correlation. It is R, which is the rank correlation numerical value. It is equal to 1 negative 6 times summation of d square over n square minus 1. Okay. Now let us come to the case of tied ranks. The formula for tied ranks is rank correlation R is equal to 1 negative 6 times within box brackets summation of d square plus m cube minus m divided by 12. We keep on adding all the tied cases, entire thing divided over n times n square minus 1. So let me just highlight the part which makes sense to us. If you remember, this part of the formula remains the same. This is exactly what we did previously, so no changes in this part of the formula. What actually does change is to the term summation of d square, we now add m cube minus m over 12 in a summation. Let's take a simple example to understand. Let's say our tied ranks were 1, 2, it would be 1, 3, 3, 3 and 5. So if the ranks are 1, 3, 3, 3 and 5, these three are found to have the same rank. How many times have the rank been repeated? They have been repeated 3 times. So this term becomes 3 to the power 3 negative 3 over 12. That becomes 27 negative 3, 24 divided by 12, and it comes out to be 2. Any questions? Let us take another example for the tied ranks. It will make things easier after that. Let's say the tied ranks are 1, 2.5, 2.5 and 4. In such case, when the ranks are 1, 2.5, 2.5 and 4, then how many tied cases are there? 2 in all. So this term would become 2 cube negative 2 divided by 12. So that is 8 negative 2, 6 over 12, 1 over 2. Okay, the rest remains same, nothing else changes. With that, we'll take questions. If anybody has any questions, feel free to ask me. Anyone? Any queries? Okay. Thank you then. See you. Have a nice day.